Hi there, welcome back to another Study With Me session. My name is Amy. I'm the head maths tutor at Pinnacle Coaching College. So what I've got for you today for our extension to students, it's another revision module on complex numbers. So the idea behind this module is to show you some more extreme exam questions in this area, and if you're preparing for your first assessment, your first HSC assessment, I'm hoping this will push you to your limits a little bit and get you to learn some of the harder techniques, or how to, not so much harder techniques, but how to attempt and tackle harder exam questions in this area. So I mean, there is a range of questions in there, but you'll find that the harder questions seem to draw on some of the same concepts. And I highly recommend you working through this module with me. So, as in, with every question, pause the video, attempt it yourself, and only look at the answers after you've made some attempt. And I think you'll just get so much more out of it. And I will recommend this sort of like, you're at the end of your studies. You need that extra push, extra challenge, just to make sure you're ready for the upcoming assessment. I think this is what it's for, right? To challenge you, to push you to your full potential. Let's get straight into it. All right, so let's start with a baby one first. Always start with a baby one. This one's not hard actually. Having said that though, I realized this over the many years I've been teaching. When I say it's not hard, most students struggle with it, right? They're like, why? You said it's not hard, it's so hard. And I think this is one of those. When I say it's not hard, I think it's because for me it's so obvious, but it might not be as obvious to you. All right, so the first part. We're given that Z is that. Find the modulus. So now, why I found this fairly easy is because I obviously know or understood what this notation means. And I think those students who really struggle with this question is they don't fully understand what they're working with. Okay, so let's understand what we're working with. So remember, a complex number is anything in the form x plus iy. This is your x, this is your y. Yeah, everyone see that? So if you're finding the modulus, you are doing square root of x squared plus y squared. Okay, so alright, so that's what we're doing. Let's expand this. Okay, so now cos 2 theta squared sine 2 theta squared adds up to 1. So 1 plus 1 is 2. And then, obviously, if you look at your current result and what you're shooting for, we've got a double angle changing that to a single angle. So I'll call upon the double angle rule, specifically this version of it, since we're shooting for sine theta. And that's another important tip from me. If you're proving something, don't blindly do it and then check at the end to see if you've got it right. Yeah, there is no value in that. Keep checking. See if you are on the right track as you are doing it. Especially when it comes with trigonometry. When it comes to trigonometry, because there's so many identities out there, right, that you can potentially use. You need to pick and choose the versions that's going to work to your advantage. So don't waste time going in circles. Keep checking where you're going and choose selectively. That's it. All right, so that's nice and easy. I promise you this will be easy. All right, the second one. Alright, so we're going to show that the argument is that. Now, the first one I find most students can eventually figure out. The second one trip up a lot of students, and I can see why, because it's nowhere near as straightforward. But your starting point is, well, how do you calculate an argument? So if you think about the complex number, right? So let's think very briefly first. So I won't use theta, just not clash. X. I feel like my computer is dying a little bit. There we go. Okay. If you want to find that angle, which is the argument, right, you use tan alpha, in this case, is y on x, or alpha is inverse tan y on x. Okay, so it's just your y and x in this case is these two things. So with that in mind, I'll say tan the argument of z, whatever that might be, yeah, which we're trying to work out, is y, which is sine 2 theta on x. Okay, that's the starting point. So if you were stuck on the starting point, here it is. See how you go, see if you can show the results. All right, so I'm going to keep going. Now, keep checking. Actually, I've got the question. Checking what you're trying to get to. You see it's pi on 2 minus a single theta. That's telling me I should break up all the double angles. And I'm going to use the same double angle rule as before. The reason I picked that is I want the 1 to cancel out. Yeah, you see the 1 cancels out. That's what you want. And that's generally how you should be picking the version of double angle rule for cosine if you haven't figured it out by now. All right, so cos theta on sine theta, which is cot theta. Now, if you got this far, well done. You're only actually one step away from getting to the right answer. And this is where you need a very good knowledge of the trig identities. So I don't know if you know this, but cot theta is actually equal to tan pi on 2 minus theta, or 90 minus theta, and vice versa. It's a complementary angle identity. And there's a similar one for sine and cos, sec and cosec as well. I won't get into that today. All right, so that's what I'm going to do. So therefore, tan arg z is equals to cot theta, which is tan pi on 2 minus theta. All right, so therefore, arg z is pi on 2 minus theta. All right, that's it. Very simple, right? I promise you it's simple once you know what you're looking for. All right, so to summarize, first up is just finding the modulus. So modulus is Pythagoras, and that's what you do. And a bit of trig identity magic, you'll get there. And the second one, arguments are arguments using the tan ratio to help you build that, and then just using the complementary angle identity to help you switch it up. All right, moving on. You can see it's jumped from maybe a level 3 to like a level 10. All right, so these type of roots question gets a lot of students, and that's why I love doing them, because you know it's kind of hard, but at the same time, they're all very standard. Like there's a certain steps about them. If you know those steps, it's actually very simple. All right, so the first one. Right, this first one is actually pretty easy. We want to find the fifth root of unity essentially. So z5 equals to 1. So what I'm going to do is, okay, I'm going to let z equals to r cis theta. So r, jumping ahead of myself. Alright, so sub that into there. The moles. And 1 is 1 cis 0. Alright, so r to the power 5 is 1. 5 theta is 0 plus 2k pi. Yeah, that's to generalize the solution. just do it like that. Okay, so theta is 2k pi on 5. All right, so then basically your roots are going to be in this form. So roots are in the form 1 cis 2k pi on 5. All right, we just need to figure out what they are with different k values. So just start with k is 0. Alright, so that's it. Now what you should notice with roots of unity is that one is always a solution, and then everything else come in conjugate pairs. And I will just briefly mention this as well. They are on a circle of radius 1, so 1 being an answer itself, and you should be able to draw them evenly distributed where they are 2 pi on 5 units apart. Okay, so literally dividing the circle into 5 equal portions. That's how roots of unity work. All right, I thought I'll point that out. Not that you need to draw this, but that's what it is. Use that as your cross check or to quickly find roots if you need to. All right, so the second part, show that it can be factorized in that form. Okie dokie. Alright, so to start, let's start with our roots. Actually, before I dive in, I want to show you an identity first, because that's going to help you with these type of expressions. So if I have z minus w and z minus the conjugate, when you expand it, it looks something like this. And oops, that was meant to be a plus, minus, hold on, got my sign wrong. There we go. Minus, yes. Okay. Alright, so you should hopefully know these identities. When you add a complex, if its conjugate is 2 real parts. And when you multiply complex with its conjugate, it's modulus squared. Alright, so this identity is actually going to help you with this part. So we're going to start with the fact that this factorizes into these 5 things. Yeah, because we just found all the roots. So z minus 1. Okay, and they are in conjugate pairs, right? So it's like this situation here. So cis 2 pi 5 and cis minus 2 pi 5 are conjugates of each other. All right, so then from here, I'm just going to use this identity to help me expand. Makes it heaps easier. So that first block there is z squared minus 2 real part modulus square. Yeah, 1 square. And then same with the second one. So z squared minus 2 real part plus modulus square. That's it. All right, that's pretty much what you see there. All right. Moving on. Whoops, wrong way. The third part is to show this. Oh, firstly, it says hence. So hence, remember, means using the prior participle assist you. to show this, and then hence find the exact value of that. Now, very careful here, because there's actually many ways to find this. You can use some of the roots, I think, for this one, yeah, to get this. But it does say hence. Hence, you're forced to use the prior part to help you. So just be careful with that. What I'm going to do, I'm just going to copy the prior part as well. There we go. Okay. All right, so the trick here is if you use the factorization, what you could do is something called equating the coefficient. Now, because this thing expands into a massive thing, so I'm going to try to explain how I'm going to sort of expand it partially in my head, so to identify the term. So what I'm going to do is using that. So I'm just going to expand this into two parts. So z times d2. And then minus 1 times these two. Okay. Now, what you're looking for is a term with these things in it. So now if you sort of think about it, actually look at this part because that's a lot easier. All right, so it's the expansion is going to go like this, right? It's going to go, well, minus 1 times everything you expand this. And when you expand this, it'll be z squared times z squared. That's a z to the power 4. Z squared times z, so that's z cubed. Z squared times 1, z squared. And then you just keep matching up that, 1 times dot, dot, dot. Okay, so there are two terms you can potentially look for. One of them is the z term. So if you look at minus 2z cos 2 power 5 times 1, yeah, that will get you a z term. Okay, and that should only have cos 2 power 5 in it. The other one, I'm just looking at this now. If you look at z squared times that, that will also get you a cos 4 power 5. So z cubed term should also work theoretically. But I'm just going to stick to one method. All right, so consider the z term on both sides. Okay, so on the right, I'll do the first chain first. So to get the z term, basically there's only one way to get it, right? Because if you have z squared times anything here, that's going to be more than z, so that's not good. That times everything here, it's going to be at least z. And then when you times the z outside, that's not going to be a z term, right? And then if you do 1, that's what you're looking for, all right? So 1 times z. Yeah, that's a z term on the first expansion. On the second expansion, okay, you have to do sort of imagine it a bit. So I want to go minus 1 times that times that. Yeah, so 1, 2, 3. Okay, the other one is minus 1, 1, and that middle term there. So imagine you're going to the shops, right? You're picking one from each basket. The first basket is minus 1. You can't get rid of that one. The second basket, you have to pick something times something that will get you a z term. That's all I'm really doing here if this is a bit confusing. Okay, so minus 1, 1, that. Okay, so then now on the left side, there is no z term, right? So it means you have 0 z on that side. So I'm just going to clean this up a bit. So that's plus 2. Now the idea here is very, very simple. Because they are meant to be expressions for exactly the same thing. So the coefficient of like terms should be the same. So the coefficient of z is 0 on the left side. The coefficient of z is 1 plus 2 cos 2 pi on 5 plus 2 cos 4 pi on 5. Yeah, they should equate. And now you just have to make this look like that. So move the 1 divided by 2, that's it. Alright, so it's not as hard as it looks. Look, if you're really struggling, do this. Actually expand everything. I know it's painful, that's why I didn't want to do it, but expand everything. You're looking for the z term and you should find these 3 terms. Alright, so that's another trick. Alright, so going back here, actually I have the question here, and then hence find the exact value of that. Now this is a very common follow-up to that identity, and the trick here is because that's the double angle of this one, you can build a quadratic. So I'm going to show you how that can be done. What I'm going to do is just replicate that chunk there. Alright, so I'm going to start with this guy. I'm going to apply the double angle rule. So the double angle rule, remember, looks like this. So in this case, cos 4 pi on 5, which is 2 times 2 pi on 5, is 2 cos 2 pi on 5 squared minus 1. All right, so I'm going to stick that in there. And then you see a quadratic forming. And then just multiply everything by 2. Put that into the quadratic formula. Now, it doesn't make sense for this ratio to have 2 answers, so you do need to explain yourself a bit. So you can say, well, since cos 2 pi on 5, it's a positive value because this is acute, therefore cos 2 pi on 5 is minus 1 plus root 5 on 4 only. That's pretty much it. Yeah, and that's actually how you tackle a lot of these similar type of questions. So hopefully that helps you. Alrighty. Let's have a look at the next one. What have we got here? Question 3. Alright, so we're trying to prove that. I think once we get into it, you'll realize this thing is actually not too hard. But at the same time, keep your eye on where you're shooting. Because trig equations and trig ratios, there's just so many identities. You need to be careful with what you then choose to use to simplify your thing. All right. So what we're going to do, we're going to start with that. Yeah, so 2 on 1 plus z. Now, just sort of thinking out loud here, this is how I'll go about it. So after doing the first step, actually pause before you go, oh yeah, just go times the conjugate of that, right? Because the conjugate of that is not clean. It's messy. So I kind of want to avoid doing that unless you want to spend a lot of time simplifying your expression. I'm just sort of planning out, I need half theta. So maybe it's a good idea to start using double angle rules at this stage, just to clean up the expression a bit so that it's just easier to simplify. Okay, so I'm going to use the fact that, well, cos theta should be just 1 minus, I'm going to use, actually I'm not going to use 1 minus, I'll use the other one, 2 cos theta on 2 minus 1. I'm going to pick this one because then that can cancel out of the 1. That makes it a lot easier to work with. And then sine theta will just be the double angle rule. Okay, so let's do that. And then, see, that's what I was looking for. All right, so notice that 2 cos theta on 2 is a common factor. Let's factorize it out. All right, so actually that cleaned it up a lot. Yeah, because you don't have the extra 1. That 1 creates a lot of chaos. So now I can multiply by the conjugate. The 2 cancels. Alright, so when you multiply the complex number with its conjugate, you get modulus square, or in this case, it will just be that squared plus that squared. I might need a new page for this. Okay, so then from here, sorry, I'll just remember it. So on top, we've got that on the bottom. Okay, so that's just 1. Okay, and then split this up. That's it. Alright, so it's easy when I do it, I know, but I've also tried to explain my thinking process to you, because for you, that's actually what's more important. The result is unimportant. My thinking process, I'm hoping, is what you're learning from. Yeah, always look at what you're shooting for and use that to guide your decisions around how you're going to simplify this. Because imagine if you just right up front try to multiply by the conjugate, or maybe when you pause the video, that's exactly what you did, right? So you can spend a lot of time going in circles, or maybe you start putting in the T formula. I mean, you can absolutely do that as well. But I would say this is probably one of the fastest way to get there. And I looked at the result before I started, right? And keep checking, am I going down the right path? I know I need theta on 2. How do I create theta on 2? Yeah, that's how I sort of think, okay, I need double angle rule. Where or when I'm going to apply those double angle rule. All right, so I hope this helps you. All right, next. This one's interesting. This one is not hard per se. I know I say it's not hard, and then you probably tried it and came back and said, it was so hard. Okay, it's not hard if you understand thoroughly how addition of vectors work and how they relate to each other, because that's actually what this is testing. So before we even dive in, I want to draw your attention to this. Okay, let's say we have 2 vectors, z1 and z2. Let's call them A and B. You're obviously investigating to a certain extent z1 plus z2 and z1 minus z2. So let's draw up our typical parallelogram situation here. So this vector, let's call that C, is your z1 plus z2. And this vector pointing towards Z1 is Z1 minus Z2. Having this understanding is absolutely crucial to be able to understand this problem altogether, because if you don't know where these factors sit with respect to each other, you're kind of like, well, where do I start for this? Okay, so the question is, these two are complex numbers so that when you have this divided by this, you get 2i, which is purely imaginary. Now that itself has some implications I'll show you very soon. You want to then prove that is true, which is basically these two are equal, implying that's a rhombus. Well, so going down that kind of thinking, okay, if that's a rhombus, and I've got information on the diagonals, essentially, diagonals of a rhombus are 90 degrees, right, or perpendicular. Okay, so how does that information give me that? That's the chain of logic. Okay. So what I'm going to do, I'm going to copy this. Okay, so then the argument of Z1 plus Z2, Z1 minus Z2 is the same as, that is terrible, argument of 2i, yeah, because it represents 2i, and 2i, it's here, right, 2i, yeah, so that's a vector with a 90-degree angle, so pi on 2. And remember, when you divide, arguments subtract, so that means the difference between the arguments of these two vectors are 90 degrees. Okay, so now I would say in this particular exam question, I'll definitely draw this diagram, right? How else are you going to explain yourself? It's hard to explain yourself. Explain with diagram, okay? So I will say, okay, so this means BA is perpendicular to OC. Yeah, that's what it means. All right. So then from here, all right, so they're perpendicular, then you take a step back, right? That implies this is a rhombus. Therefore, OACB is a rhombus. Let's write it. Right, so perpendicular bisectors. You kind of know that it's bisecting without proving because it's a parallelogram at the least. So they naturally bisect, and then you've got that perpendicular as well. All right, then the final step is that means OA is the same as OB, right? Equal sides. Meaning the modulus have to equal, right? Because they represent, yeah, the modulus, the length of the sides. All right, so that's it. I mean, if you look at the question, it's not very obvious that's what you need to look at, and I think that's why you need that understanding to be able to connect the dots together. Yeah, so I think this diagram is very, very important for you to understand, sort of digest, and think about the different ways it can apply as well. All right, so it goes then, if alpha is the angle in between these two vectors, show that. All right, so I mean, given that there's a second part, you're sort of following, okay, well, this information obviously still applies, and we already established it's a rhombus, so we know those two things so far. So what I'm going to do is let's copy that again. Getting more and more messy. Okay. So this time we know this guy is alpha. And we are trying to prove tan alpha on 2 is a half. All right, so proof tan alpha on 2 is a half. Okay, so firstly, I'm looking at tan, I'm looking at alpha on 2. Look for those two on your diagram first. So I'm thinking, okay, hold on. Rhombus means that bisects the angle. So these guys are alpha on 2, right? So I'll start with that first. So angle COA is equal to alpha on 2. Okay, so then from here, the other question is I'm looking for tan. And tan normally works in right angle triangle. So that's kind of the direction I'm going to go for because I know that this is, let's call that M, right? This is a right angle, right? So let's do it here. So this is alpha on 2. We know that this is modulus of Z1. I don't think we need that because tan use these sides. All right, so in a rhombus, the diagonals bisect each other as well. So these guys are going to be half of the modulus of Z1 minus Z2. And this one is half of this guy. So half of modulus of Z1 plus Z2. Right, so I'll just comment on that. Okay, and then now I've got an expression, right? So MA on MO. Keep doing that. Okay, so then from here, the half cancels. So you have the modulus of that on that. Now, which can be combined as one thing. So remember, the modulus of a division is the same as the division of the individual modulus together. So then, remember what this represented. This represented 2i. So the reciprocal of that is 1 on 2i. So you're looking for the modulus of that, which is just a half. That's it. Easy, right? So it looked complicated until you fully appreciate the information and the relationship, how it sits in a parallelogram, which was then proven to be a rhombus, and using that information to build out what is required in this question. So I hope this is really helping you in terms of how to break down these problems. All right, I've got a final one, which is a HSC question, by the way. It's one of those things that might give you a heart attack when you first look at it. All right, so emotions will look at that. Oh my God, so many things and everything looks so complicated. And you know, I won't lie, it looks complicated. But once you get into it, it's not too bad. So let's start with the first part, baby one mark. Alpha is that, show that. Okay, Okay, so let's copy that. All right, so let's just use it. I'll say, don't get too worked up by how complicated some of the 4-unit questions look. I mean, most of the time they do look complicated for sure. And just take it one part at a time. Just think about, okay, they want me to show this. Where am I going to, source information to establish this result? And once you sort of work through it in that manner, you'll find that everything is pretty manageable. So the imaginary part disappears. That's it. And you'll get good at that. If this is like your first HSC assessment, you'll find that how are you seeing all of these relationships? How can you just see it and know that's the thing to do? It comes with experience. I can say of you right now, your abilities compared to when you're about to the HSC, you'll be so different. I see that change in all of my students. By the time they go do HSC, they're gunning this down faster than I can, right? So you will get better. All right, don't let the first assessment sort of put that much pressure on you. It's your first time, you've only done this for a term. You won't be able to develop that spidey sense as to what you're supposed to be doing, and you will get there. All right, so don't worry too much. Just soak it all in like a sponge, and that's why I'm doing these videos to show you the techniques. Yeah, so start soaking in these techniques and remember them for future use. Okay, so that's it. First one done. Second one. All right, so you're given, let's see, is that. Now I'm going to use this opportunity to teach you how to read an exam question. It goes, by summing the series, prove that, and 3 marks. So meaning there is a level of toughness to this. Okay, so first of all, let me just copy this over. Now, so what's interesting is this. Now, if you look at this, you're like, oh my God, how is that that? Right? But it does say by summing the series. So that's probably where I'll start. And don't overcomplicate it, because sometimes, overcomplicating things will get you in a bigger sort of in this massive circle. So I'm just going for the most simplest understanding of how to sum a series, right? How do you sum a series? If you want to add 1 plus 2 plus 4, let's say, so you treat that as a GP, for example. Remember, first term is 1, common ratio is 2, and then you need to figure out how many terms there are. And then we use the SN. We'll use this version of the formula. You'll see why we use this one sec. Okay, so I'm going to use that very basic summing of a GP to work this out first, and then we'll see where that takes us. If it doesn't work, then we'll find another way. So the first term here is that one. To get to the next term, you can guess the power is sort of increasing by 1. So the ratio is alpha, right? Or if you're not sure, just divide it through, right? That divided by that or that divided by that, that should tell you what the term is. And then there are how many terms? So that's n terms. That's another n terms plus 1, so 2n plus 1 terms. Okay? Actually, that's a little bit confusing. I'll just say 2n plus 1 terms. Okay? All right, so C is equal to, using this formula, A, so alpha minus, so the power of minus n, 1 minus alpha to the power of n, meaning the number of terms, 2n plus 1. And some of you might not even have even done sequences and series yet. That's okay. I've given you the formula right here. You can just use that. Okay, so that's what it looks like. Now you can see why I picked this formula, because you see it's 1 minus alpha. That's actually what I wanted down here. Okay. Then you stop. You're like, oh no, it doesn't look the same. Of course it doesn't look the same. It's 3 marks. It can't be that simple. So this is where I'll study the expression. You look at this, right? There's a conjugate in there. Why is there a conjugate in there? Okay, so if this is true, does that mean to get that in the denominator, I will say I need that top and bottom, right, to simplify this. So that's where I'll go next. Okay. And I'll actually partially expand the first part. See, 2n minus n, so n plus 1. So you see how I'm using the question to guide me? Now, right now, when I first did this, even then I wasn't like, is this gonna get me to what I want? I don't know. You just keep trying, right? So it looks like it's in the right direction because the bottom is right now, yeah. The top is not right, so we need to fix that. Okay. Now the challenge is how the heck do I deal with the conjugate? Now in this case, going back to what alpha stood for. Alpha stood for cos theta plus I sine theta. Basically cis theta, right? So the conjugate is cis minus theta, which is, by the way, the same as putting it to the power of -1. That's powerful stuff, man. Turning a conjugate into an indices form, that means you can change this. Okay, so not a good idea trying to expand this out like this. Let's see if I can copy that. That's better. Okay. Okay, so expand. And then I'm just going to regroup it. I have the question in front of me, so I'm just going to regroup it so that these two guys are up front. And then these two guys are inside. So n plus 1, that's that one, and minus n plus 1. That's what I needed. That's it, isn't it a piece of cake? Yeah, 3 marks. But I can see how a lot of students will get stuck because, even when I did it, there was a bit of doubt. Oh, is this right? Is this going down the right path? And you'll find out a lot of 4-unit questions are like that. You're kind of going with your gut first. Yeah, once you've done enough exam question, you realize, okay, if they're pointing me in that direction, it should be right. So you just kind of keep persevering. And then if you persevere to the end, it's still not right, then you go back and revisit, okay, is my starting point correct? Are there things I should change up? I think go with your gut. Once you've got enough of a good instinct, you'll be right 80% of the time. And you just have to figure it out and persevere to the end. All right, let's go back to the question. All right, what do we have? Deduce from part 1 and part 2. That is true. Okay, so what I'm going to do is I'm just going to, actually, I'll comment it on here because it's going to be hard for me to copy this whole thing across. Deduce means using the prior past to help you sort of connect the points together. So, if you look at this, right? First of all, you've got this. Okay, so I will definitely think about, okay, well, C is that. Okay, so I can start to see, okay, these things have to come from that chain. This guy has to come from that chain there. Yeah, and then you've got that as well. So if you look at the way these two are combined together, They are basically like that. So that's probably where I would think it applies. Okay, so with that in mind, and you can always do this part without even proving the previous part. It's just connecting the pieces together. Okay, so using part 2. So I'm just copying this first. Okay. All right, so basically that adds up to that. Okay, so on the left-hand side, now remember what alpha is. Alpha is cis theta, right? So that's cis minus n theta, cis. Now I don't want to write out too much stuff. Okay. Now each of these components are going to be cos plus I sine, right? So in fact, I'll write it. So cos n theta, yeah. So the negative, I'm just going to treat that as a conjugate. So minus I sine n theta, okay? And then you get to that. That's cos theta minus I sine theta plus 1. I'm just going to keep them in brackets so you can see. Okay, so you can see that the first half is all the conjugates and the second half is all the positive ones. And all the I sine theta kind of disappears. Okay, so you get 2 of all the cosines. Yeah, that remain. So that's pretty much the left side. And then on the right side, I might do that on a new page. Okay, on the right side, I'm going to use the first part. So the first part said that's 2 cos k theta. Okay, so that's 2 cos n theta minus 2 cos n plus 1 theta over. So this is 1 minus cis theta, 1 minus cis minus theta. All right, so simplifying that, I'll just do it on the side. Okay, so I'll just quickly explain this. I did it very quickly. So basically you have sort of adding a conjugate pair. So you just get two real parts, and then basically if you have complex number times its conjugate, you get modulus squared. And then I add that in front, you get that. So then from here, now keep checking against the question. So I'm checking it on my table just to see I'm on the right track, but that's exactly what you should do as well. So I'm going to factorize the 2. So the 2 cancels, and then that's the right side. Yeah, that's it. So therefore, now this is where just copy the question. It's always a nice habit when it's a show, deduce type of question. The answer sitting in the question, and you know, for someone who's marking this, even though you think you've kind of have fudged your answer, just copy the final result in as is in the question. Because sometimes imagine the tired teacher who's trying to mark your exam and probably read like, you know, hundreds of others. They might miss it. And I have had students who actually got full marks on something that they knew they dodged. So that's a little trick there. Use to your advantage. Copy the final result in always, whether you've got it or not. But that's it. Moving on. All right, show. This is independent of n. Now, keeping in mind what you've just proven. So you've just proven this identity. I'm just going to copy. Now, I know it doesn't say hence, probably should, but you just use this identity, right? So you can see that theta should be pi on n. All right, so before I continue, I just want to focus on simplifying the right-hand side first. So that's cos pi minus cos, cos pi plus pi on n over 1 minus cos pi on n. Because we need to plan out how we're going to simplify this. So cos pi is just -1. Now this guy here, basically, if you think about what cos pi plus theta is, yeah, pi plus theta means you're in the third quadrant, which is equivalent to negative cos theta. Make sense? So that converts it into negative cos pi on n. And you can see it cancels out. -1. Okay, so the right-hand side cancels out to something incredibly simple. So I am going to copy that. Whoop, that was not what I wanted. Yep, let's copy that. Okay. All right, so it's got a little bit messy, but that's okay. All right, so coming back to that, that's what we're trying to prove, right? This thing here. All right, so therefore, so I just copied that for our reference. So 1 plus 2 . is -1, right? We've just proven that. So cos upon n, cos, and you can use your calculator to check this, right? Let's say n is 5 or something. See if it actually adds up to what we are proposing. So -1, move the 1 across, so that's -2 over 2, so -1. All right, so therefore independent of n. So it shouldn't matter how many you add, in other words. And that's it. That's the last one. How was that? So just to summarize. So the first part, very basic. I mean, you should be able to do that very simply with your current knowledge. The second one, take the hint, sum the sequence first, and just kind of persevere and use the question to guide you in terms of what you need to multiply or manipulate to get there. The third one wasn't too hard as a follow-up from the second question. You have to figure out how to get those components. And the last part is a very obvious application of the previous part. Alrighty, so typical exam question, by the way, it's how to break up the parts, understand how the parts connect together. Even if you have to just answer the subparts to get there, yeah, grab as many marks as you can. And I think that is it. I've got no more questions to torture you. Actually, that's a lie. I've got a lot of questions, but you know, that's enough for today. Okay. But yeah, if you want more deadly questions, let me know. You can email me. I can send you some more. Or maybe like this is plenty of practice. If you saw this like the night before your assessment, I hope I'm not freaking you out a little bit here. In any case, if these type of videos are helping you, let me know by liking the video so I know. I've also linked down below the previous complex number module I did, which is just dealing with exam questions on vectors. So if vectors is your weakness, that's where you should check. And otherwise, best of luck with your first assessment. I hope everything goes well. You can always get in touch with me via Facebook, email, or our website. In fact, I've got a lot of revision material uploaded onto our website, so check it out if and when you need it. Best of luck. Bye for now.